Yes, ma'am, you clearly audible. You can start.
Okay. So initially, let us start with the failure classification. Failure classification, it means that when I can say that yes, my transaction or my system has got failed, or which can be a problem. So whatever failures are there, so these are categorized into number of categories are there. So there are main three categories are there. That is a transaction failure. It means whenever I'm performing any operation, if that problem during that operation any problem is there, or there is a system crash, or whatever disk wherever I'm storing my data that got failed. Okay, so these three types of the failures can be there. So let us deal with the first one, that is a transaction failure. So transaction failure, this can occur because of two reasons, or there can be two problems when I can say that a transaction got failed. The first one is a logical error. Logical error, it means that whatever my statements or whatever operation I am performing, that is violating some constraints. For example, right now I'm having 1000 into my account and I'm trying to withdraw 1500. It means whatever transaction I'm executing, that is a false, and whatever statements I have written, that is causing an internal error. Okay, so this wherever any logical problem is there because of which system cannot continue with the transaction, such logical errors, this can be a first reason for a transaction failure. And next one, system errors. Just like whenever we are active in the system, it means right now operation is going on, and during that period, because of some reason, my database server doesn't allow me to continue with the transaction. It means because of some system problem, that server is not available. If I'm using a machine, that is it means a computer machine, unnecessary power failure, that also can cause a transaction to fail. Or if there is a rollback, it means deadlock is there, and because of which my own transaction only got selected as a victim and need to be rolled back. So it means there is no any logical problem is there, or whatever my statements I have written, all these operations are correct and allowed by the database, but because of system's own problem, my transaction cannot be continued or cannot be completed. So it means system errors also can be a problem or can result into a transaction failure. Next, a system crash. System crash, it means that this is actually a physical harm to my machine. It means right now a power failure. It means I'm performing some operation, some power failure occur, or at the server if I'm facing any problem, that is a physical problem, not a system or any software problem, because of which my hardware, any of the hardware doesn't working, or software whatever I'm trying to access, it has crossed some limit, and because of which it is facing some problem. So it means whatever system's own major problems are there, hardware or software, that also can lead to a transaction failure. So here we are learning about a fail stop assumption. Fail stop assumption, it means that whatever my non-volatile storage is there, these are always preserved. It means, for example, right now I'm using a laptop, and on C drive I have installed my machine. So we know that there are two types of the memories are there, RAM, ROM, etc. But RAM, it means that wherever my OS is getting loaded and whatever programs I open, that will be opened into RAM. And whereas I'm having a secondary storage also. Secondary storage which can be in hundreds or hundreds of GBs and TBs, where I can store my data permanently. So it need not to be loaded into whenever I'm starting my machine. Whenever I'm requiring, we can use that data. So the fill stop assumption says that whatever data we are storing onto the secondary storage is there, that is not get corrupted by this system crash. Even though today I'm facing a RAM problem, that is my RAM is not working, my OS got corrupted, I can go for a formatting of my machine, but whatever data available on my secondary disk is there or secondary drive is there, that will be available. So there are options with the repair of drive, etc. So by using that I can access that data repeatedly. So it means fail stop assumption says that whatever secondary storage data is there, that can be available even after there is a system crash. So here, now again, database systems have numerous integrity checks to prevent corruption of disk data. Yes, it means here, whenever we are trying to perform any illegal operation or not allowed operation, so database is having its own ways to check the correctness of data. So those we know that these we are calling it as a integrity constraints. So this will prevent us to corrupt the data. For example, if I'm trying to say that right now 1000 is my amount available in my account and minimum limitation of account is 1000 and somebody trying to withdraw that 500, so 500 we cannot withdraw from a 1000 balance because my minimum limitation is 1000. So that integrity constraint can be applied on my database, that is on secondary storage, by using some rules. Then it means this will not allow to perform that operation and will abort my transaction, and hence my database will be in a consistent state. So this was the integrity constraints. Next, disk failure, a head crash or similar disk failure destroys all part of disk storage. So this can be a major problem. Wherever remaining, it means previous problems we have seen. There are ways to recover from those errors or failures, but when it comes to the disk failure, so this is impossible to cover. It means there are no ways that we can recover our data from a failed disk. Okay, so this can be a major harm to our database. So destruction is assumed to be detectable, that a disk drives are checksum to detect failure. So here, whether my disk is failed or any corrupt data is corrupted, that can be checked by using a checksum. Checksum, it means that these are kinds of parity bits which are set or reset, and based on that whether it is checked whether still that checksum is available, etc. So this is the way to detect the failures. Next, recovery algorithms. Recovery algorithms, it means that if there is a failure, then how we can go for recovery. Recovery, it means that now my system has failed. Now how, which are the ways through which we can get those data which was there available previously. Okay, so this was required. So for this purpose, we always use a recovery algorithm. So let us see an example. For example, consider I'm having a transaction TI which transfers $50 from account A to account B. Okay, so this is my current transaction. So for this purpose, we need two updates. That is, subtract $50 from account A's balance and add that account balance to the B's account. So in this case, transaction TI requires updates to A and B both. It means to both of these account database operations need to be performed. That is, both changed values must be returned to a database. So here, a failure may occur after one of these modifications have been made, but before both of them are made. Consider both A and B is having the before transaction amount $100 and $50 from A need to be deducted. That is, A's new value to be 50 and B's new value to be $150. So A's value is modified, that is $50 has been made, but B's value 150 yet to be modified. Then in between, if there is a failure. So it means that here we know that there is a property of transaction that these are atomic in nature, but when it comes to the modifying the database, how we will know that yes, transaction has been completed, but how we will know that out of two modifications, only single modification is done. It means transaction is committed, all the changes are done, asset properties also followed. So in that case, whenever a changes need to be made to a database, how we will know that there is a pending write of B is there, or A is only done, or A should be undo, etc. It means whatever these updates are there, how we should know whenever my system restarts, when it will know that A is modified and B is removed. Okay, this was the problem. So modifying a database without ensuring the transaction will commit may leave the database in an inconsistent state. So here, if right now A's modification is done, B's modification is yet remaining, and I don't know whether transaction is committed or not. Okay, transaction may commit, transaction may not commit. So this also can cause a database into inconsistent state. Or not modifying the database may result in lost updates if failure occurs just after the transaction commits. Okay, transaction is committed, but during the updates, system failure or failure whenever we are performing a changes. So for this purpose, we need to take two steps for a recovery algorithm. So recovery algorithm always performs recovery by using the two steps. So there are, it means two parts are there for the recovery algorithm. First part is that actions taken during normal transaction processing to ensure enough information exists to recover from failures. Okay, this means that whenever I'm executing a transaction, at this point only I will make sure that whenever I'm performing a transaction, my system may fail at any point of time. So whenever system resumes, it should have enough data so that it will know that those operations were done. Okay, so here whenever we are executing normally a transaction, this will keep a track of its own actions. माझं ट्रान्झॅक्शन कमिट होईल का नाही ते पण मला नाही माहिती. माझी ट्रान्झॅक्शन इट मीन्स एक्झिक्यूट असताना फेल्युअर होईल का नाही, बिकॉज वी कॅनॉट check a failure. Yes, we can guess that system may get failed, system may get failed. At which point of time, when it is getting failed, how it is getting failed, that can be a problem. But here, if whenever we are executing a transaction, the system, that is a recovery algorithms, make sure that whenever it is executing a transaction, it should have enough data. Okay, enough data or information exists to recover from failures. Okay, so this was the first normal steps which are taken in order to recovery algorithms. And second step is that actions taken after failure to recover the database contents to state that ensures atomicity, consistency, and durability. Okay, so this means that few steps are taken before failure and few steps are taken after the failure. Okay, whenever we are executing a transaction, this recovery algorithms will keep a track that which modifications are done, which operations are done, that information is preserved, and whenever system resumes after a failure, at this point, this can access that information and make a conclusion whether to perform changes to the database, whether to abort the transaction, or which steps to be performed. So that actions are always decided after the transaction resumes after the failure, and it will make sure that whatever the properties, that is atomicity, consistency, and durability, these should be attained. That is, it should be followed by the existing transaction. So here you might be thinking, what about isolation? So isolation, it means that this was a concurrent access problem. Here, whenever we are resuming the transaction contents, at that point we are not actually executing the transaction. Okay, that's why here those data will be definitely accessed in an isolated manner. So that's why this property need not to be checked. Now let us move to the storage structure. So this point is a repetition. In the concurrency control also, we have seen this point. So volatile storage does not survive system crashes. For example, we are having main memory, cache memory. So these are the examples of volatile storage. As soon as power goes off, all the data will be erased. Next, non-volatile storage survives system crash. For example, our secondary devices like disk, tape, flash memory, non-volatile RAM. So these are the secondary storage devices, and this may it means this may still fail. It means it can be a case that my disk got some corrupted data, or disk has lost its warranty, etc. Any problem can be there. So this can also lose the data. And last type of the storage is a stable storage. Stable storage. So this is mythical form storage. It means does not possible. It means in theory only this kind of stable storage is available that survives all the failures. Okay, but this can be achieved or near to the achievement by approximated by maintaining multiple copies on distinct non-volatile media. So here, whatever data we are seeing that it's stored at the stable storage, this means that that data is being repeated on multiple units or multiple disks, so that even though one disk got failed, second disk is available or another copy is existing in order to say that yes, that data is not yet lost, that data is available. Okay, this is a form of implementation of a stable storage. So how we are implementing a stable storage? So maintain multiple copies of each block on separate disk. Same data will be repeated on multiple disks. Copies can be at remote sites to prevent against disasters such as fire or flooding. So if we are keeping all the copies on a same geographical location, so that location may get affected by some natural disasters also, that is flood, etc., or can be a human-made disaster like fire or any other problem. So because of which, if we are keeping all the data or same all the copies on a single place, all may face the same problem. That's why whatever the disks or copies are there, these will be remotely on a separate locations. Geographically separate remote locations, these copies will be maintained. One area is affected, other may get survived from that disaster, keeping that intention behind. Next, failure during data transfer can still result in inconsistent copies. So here, whenever we are going for a duplication of data from one side to the another, so consider that I'm having there are three copies of the same data is there, and transaction T1 has performed changes to the copy 1. Okay, so data, it means that this is going to get modified. This can be accessed by multiple transactions. So if consider there is a change to a single copy, then if change to a single copy, then that change need to be carried to the another two copies, because here we are going for a stable storage implementation, and hence whatever the changes are there, that need to be reflected to the other two copies also. Okay, for this purpose, whenever a updated data from one copy to another is being transferred, so that will be called as a data transfer. In data transfer, there can be again three possibilities can be there. That is, data from one copy to another will be transferred in terms of blocks. That is a storage unit of memory. That is a unit of memory location, 1 KB, 2 KB, etc. This can be a size of blocks. So for this purpose, can be three possibilities of data transfer. First is successful completion, that all the data got transferred successfully. Second, partial failure. And third one, total failure. Read this slide. So that is a complete block has been transferred successfully. Whatever data we have on the first copy, the same data is reflected on the second copy. So that was the first case. That is a successful data transfer. Second one, partial failure. Partial failure, it means that the first copy is also having 1 KB of data, second copy is also having 1 KB of data. But whatever data we are checking, that is not a same. It means here balance I'm having 1000 and here I'm having 900. It means any incorrect data can be there with the second copy. That can it means that was the result of a partial failure. And the third is that a total failure. Total failure, it means that if there are 10 modifications done on a first copy, then all of those 10 modifications may not be updated on a second. In case of partial, out of 10 might be 5 modifications done, 5 are remaining. But in case of total failure, none of the modifications has been done on the second write or second copy. So this can be a three possibilities whenever we are dealing with the stable storage implementation and data transfer. So how we can go for it means protecting storage media from failure during data transfer. It means what can be a solution. So there is a solution existing. So first is that execute output operations as follows. Write the information onto first physical block. It means whatever my first copy is there, we will write onto a physical block, that is actual database. Next, when first write successfully completes, write the same information onto a second physical block. So whatever our second physical block is there, write the same information. The output is completely only after the second write successfully completes. It means whenever we are modifying a database, after the commit, generally we are saying that yes, database has been modified. But when it comes to the stable storage implementation, we can say that a modification has been complete whenever the two copies, that is two copies whatever we are maintaining, all are having the same data, and whatever write we are performing, that all write it means transaction changes return to the first block as well as to the second block, and then only we can say that this transaction has been committed. Okay, so this was the approach. It means whenever a transaction is committing, not only to the local disk the changes are performed, those changes will be carried to the remote site also, and then only transaction is said to be committed. So this can be a solution whenever we are dealing with the data transfer. Second, protecting storage media from failure. It means how we can how we can protect. So copies of a block may differ due to failure during output operation. Yes, the previous case we have seen that during the write operation, these may be having, it means the copies may differ. So whenever we are saying that in this case a failure is there, then in order to recover from failure, we can carry out these steps. Find first inconsistent blocks. Okay. So whenever we are seeing that two copies are inconsistent or databases are inconsistent, then in order to keep that is a recover from failures, first we need to find a inconsistent block. Inconsistent where database state is not in correct state. Okay, so this can be it means how we can know whether inconsistent block is there. So here we can go for comparing two disk blocks. So this can be an expensive solution. It means comparing each and every data item with the other copy, that can be expensive because database size is much more. And when it says the remote site, a network cost also gets added, and because of which comparing the contents of two sites or comparing database two copies, that can be an expensive. Or we can have a better solution for this, that is record in progress disk writes on non-volatile storage. It means consider there is a copy 1 On the copy one, record which modifications are done. Okay, for example, A data item has been modified, B data item has been modified by deducting 100, or C's address is changed, or anything, whatever the perform modifications are there, record those modifications. Okay, so whenever we are performing changes to non-volatile, non-volatile is considered to be a secondary storage and causes less affected by a failure. So there it can be a flash or non-volatile RAM or special area of the disk it can be. So whenever we are saying that we need to recover another block, use the same information during the recovery to find blocks that may be inconsistent. Okay, so then if failure is there, then check that only if there are three values get modified, catch only those three blocks which can be inconsistent, because we know that there are three modifications done on database, one for A, one for B, and second for B, and third for C. Then only compare copies of this. It means check whether what is A's value. A may be having a one block, compare that block with the consistent state another side, check whether changes are done. If so, then it means this can be a consistent state. So this is a another solution. So this is used in case of hardware RAID systems. So this can be a way to recover from the failure. And second one is that if either copy of inconsistent block is detected to have an error, that is bad checksum value we are having, then override it by another copy. So second block is not inconsistent state, that is in incorrect state. Then we can copy the first side contents all into the second. Or if first one is not correct, then second copy contents to the first one. So this can be a solution. If both have no error, it means there is no any consistent state. That is, this is also having the correct value which satisfies all the constraint. Second one is also having constraint, all satisfied by all constraint, but not same. And we can say that either of the copy should be written. It means second block, whatever it is, replace this by first one, or whatever first block contents are there, copy that to the second. Next, disk access, sorry, data access. Physical blocks, buffer blocks. So physical blocks, it means that are those blocks residing on the disk. Buffer blocks are those residing temporarily in the main memory. Okay. Disk refers to a secondary storage and main memory refers to the primary storage. Physical block, uh, non-volatile storage, and buffer blocks, volatile storage. So blocks movements between disk and main memory are initiated through two operations. That is input B and output B. Input B, it means that transfers physical block B to main memory. Okay. From physical disk, we are moving to the main. Then we can say this is the input operation. So input and output operation. These operations are always takes place with respect to the database execution statements. It means whatever my database is there, with respect to that, if I'm performing input operation, it means that contents will be read from the database. Output operation, it means contents will be returned to the database. So input transfers physical block B to main memory. Output B transfers buffer block B to the disk and replaces the appropriate physical block there. And here we assume that each data item fits in and is stored inside a single block. So here it means if I'm having an integer, that is B is an integer. So here right now we are assuming that B will be a part of single block. It doesn't happen that B requires four bytes and 2 bytes are in first block and 2 bytes in second. No, here we are assuming that whatever the 4 bytes required for B are there, that will be allocated from a single block only. So this was the figure. Okay, so this was the figure which says or explains this operation. So this is my disk. Okay, disk, this is a stable or we can say a secondary storage. on which my database will be stored. So input, it means that this is my main memory. Okay, buffer, this refers to a part of main memory. Input A, it means that from the disk this will be brought into main memory. Okay, so there will be a space allocated for this, and there will be a separate local copy will be get created. Okay, this X is acting as a local copy. A is having a value 10, that value will be copied to the X. Okay, so this is a input A operation. Now this is a Y is another variable or another data item. So output B, it means that whatever the changed value is there, that will be returned to the disk. Okay, so input from the database or disk into the buffer, and output from buffer to the disk. Okay, so if and when it comes to our transactions, okay, so this was regarding the normal background operations. So but whenever we are executing multiple transactions, okay, for each transaction separate work area will be given. It means from the main memory some space will be allocated for T1, some another, it means non overlapping space will be allocated for T2. Then this whatever the data item A, it means X we have copied, a local copy will be assigned to the T1. So input A, this background operation will be given as read X, and write Y will be given as output B. So now this will perform the modifications, again write to the buffer, and from buffer those will be written to the disk. So buffer is a common area. This is a temporary storage within a main memory only. Okay. So this is a work area of T1. From the T1 this will be copied to the buffer, and from the buffer this will be copied to the disk. If before writing back the result to the disk, if any other transaction demands reading for A and B, those will be given from the buffer only. A separate input and output operation will not be done here. If those items are available into the buffer, so that can be, it means other transactions can refer to these data items also at this point. So this was regarding the data access. So read this for a minute. After this, read this slide also. This is explaining the same operation. So, okay, the same contents are explained in the slide. So each transaction TI has its private work area. Okay, private work area in which local copies of all data items accessed and updated by it are kept. So transaction may be using data item A, B, C, D or D, E, F. Any in number of items can be used by a transaction. So whenever a transaction is using those data items, a local copy will be created and for work area for the transaction, and those will be made available into that work area so that transaction can perform modifications to those data items. So whenever this local copy is created for TI, that will be called as a XI. XI it means I transaction is accessing a X data member. So transferring data items between system buffer blocks and its private work area is through readx and writex. It means from the buffer, whenever any transaction is willing to perform read operation, it will read a data item from buffer, and whenever it is completing the changes, this will write back to the buffer itself. And some buffer, those will be done with the disk changes will be done to the disk with input and output operations. Okay, so read X assigns the value of data item X to the local copy of Xi. Write X assigns value of Xi to a data item X in buffer block. So here, main thing is that whenever any transaction is performing a write operation, consider that here Y's value is getting modified. That write Y has been performed and Y's value previously was 20 and now it become 30. Then it is at all not mandatory that even though transaction T1 is committed, this change may be returned back to the disk. Okay, immediately it is not always happens that changed value as returned back to the database. Okay, this operation can be delayed also, because here whatever the read and write or input and output are done, so these are always performed in terms of memory blocks, and blocks is not a separate for each data item. And here in a block there can be multiple data items can be there. So with respect to the each data item, this output operation is not carried out. So whenever a complete block has need to be returned to a database, then only this output operation will be initiated. Yes, there are variations like immediate, deferred, etc, so that we will see later. But here I want to make sure that whenever a write Y operation is performed, it always doesn't immediately change the database. It can take a time in order to perform changes to the actual database also. Okay, so the same note is given here. So output bx need not immediately follow write x. System can perform output operation when it deems fitted. It means whenever it is willing that now space is not available, another block need to be read. At this point, this can initiate with the write operation. So okay, transactions must perform read x before accessing x for the first time. So after reading for the first time, it can go for subsequent multiple writes from the local copy, and write x can be write x can be executed at any time before transaction commit. It means this can perform changes to the local that is buffer copy at any point before transaction can commit. So this was the figure which right now we have seen regarding the data access. So this clearly shows what is meant by input, what is meant by output operation. When we can see that this is the operation done. So remaining points we will see into the next lecture. So here are some instructions regarding the ISC I wanted to give. So ISC 1 will start from the